So, welcome to the Module 3 graph analysis where we talk about eigenvector centrality. If you're not familiar with what an eigenvector is, I highly recommend to go back to Module 1 where we have Introduction to Linear Algebra and where I have a video on eigenvector and eigenvalues, which is really important, and I hope you now understand why I dragged you through that stuff, because now we actually apply it to graphs. And the idea of eigenvector centrality is to measure the most influential node in a network. This is something quite abstract because so far we looked at degrees, we looked at distance, but we also want to pin that down on a mathematical number, which is the most important and most influential node in a network. And so it's not just the node which has the most connections, but also it is a node that has connections which have a lot of connections. So especially in social networks, website ranking, and disease spread analysis, it's really, really important not just who is influential, but also who has influential followers or friends. And if you consider this in social media terms, an influencer is not just a person that has a lot of friends. It's also a person that has a lot of important friends which further spread the content. In website ranking, an important website is not just one that has a lot of links. It is one that links to other important things. That is way, way more crucial. In disease spreading, if you consider back the days of the COVID pandemic, it is not just who you infect, but it's also who the people infect that you infected already. These are really, really important things. If we talk about social networking in a more personal development, career setting space, it's also not just important who you know. It is also really, really important who the people know that you know. Because the people you know, they connect you there. You can't know everyone. The people you know, they know a lot of people, and those are the important connections. So this is also really related to the Milgram idea of 6 degrees of separation that we talked about earlier, where it's really important who knows the person that I know. And in eigenvector centrality, this is really a measurement where we can figure out who is the most influential person in that network. And to calculate that, we represent the network or the graph in an adjacency matrix. Then we solve the adjacency matrix for its eigenvector based on the largest eigenvalue. If you recall that we had earlier in this introduction video, lambda 1 and lambda 2. Lambda 1 was 7, lambda 2 was -2. So what we do here is now we solve for the eigenvector of the eigenvalue 7. And we calculate the centrality value of that and have the equation matrix A, the adjacency matrix, times its eigenvector must be equal to lambda times the eigenvector. Sounds simple, isn't that simple if you actually want to do that, but if you recall the eigenvector and eigenvector and eigenvalue discussions we had in the other video, you will see it is actually straightforward. And the important aspect here is there is now in the interpretation of eigenvector centrality, we do not have absolute interpretation of results. They are always relative interpretations. So you can only say this node is more influential or less influential compared to the other nodes in this specific graph. You cannot say, oh, we have an eigenvector centrality of 0.6 in this graph, and in a completely other graph we have an eigenvector centrality of 0.7, so the node in the other graph must be more important. No, you can only say this node is more important compared to the other nodes in this graph. And what I did here implicitly already, I normalized the range of the eigenvectors to 1, so that we actually can compare them on a linear scale. And if we look at an example, we have here the visual representation of 5 nodes and the respective adjacency matrix. In this graph, it's quite simple to see which node might be the most important node. This would be node 2, and spoiler, yes it is. The least important node here will be node 3. It has only one connection, which again has only one connection, while node 2 has a lot of connections, has actually 3 connections, and of those, all of them have another connection. So it is a really, really important node here. And if we solve that, as I said, quite straightforward to solve a 5x5 eigenvector matrix, but I give you here the solution. Lambda 1 is 1.618, pretty much average around the thumb, the ballpark range here. And we normalize that. We then have the centrality values, and we see the centrality value of node 1 is 0.37. Node 2, 0.6. So you see it's way more important than node 1. Node 3, 0.228. Node 4 and 5, again, are 0.37. So what we guessed just on the visual representation earlier is exactly the case if we calculate it. Most important is node 2, least important is node 3, because they are the least central or most central nodes respectively in this graph that we analyzed here.